Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Punching Shear Analysis on Performance of Different Types of Footings Soorya Gayathri S. M. Tech in Structural Engineering Department of Civil Engineering Thiruvananthapuram, India Abstract There are many failure mechanisms that occurs in structural members like slabs and foundation by shear under the action of concentrated loads. The action of concentrated loads is on a smaller area in the structural members. In most cases, this reaction is the one from the column acting against the foundation. Eventually the foundation will fail. One possible method of failure is that the load punches through the slab. Parameters such as bearing capacity of soil, type of loading, location of footing etc. affect the stability of the footings in different mechanisms. In this paper, the modeling and analysis of a 12-storied building supported by different footings is been studied here. The building modeling and analysis is done using extended three-dimensional analysis of building system software. The modeling and analysis of different types of footings are carried out using CSI-safe finite element analysis package for slabs and foundations by changing the bearing capacity of soil, type of loading and location of footings. Footings of the building in normal soil and weak soil are studied and compared in detail. Various parameters such as the punching shear, soil bearing capacity, bending moment, shear force, footing stress are determined. The behavior of footings in terms of the parameters are evaluated. The results are then compared. Keywords: eccentric loading, footing stress, punching shear, soil bearing capacity. Introduction: the lowest part of the civil structure or building which is in direct contact with the soil is known as foundation. It helps in the transfer of loads from the structure to the soil safely. Design of foundations are considered to be an essential factor in structural design and analysis. The foundation is an utmost part of a structure which transfers the load from the superstructure to the soil. For the study, a 12-storied building supported with different footings is modeled and analyzed here with the help of two softwares ATABS and SAFE. Types of footings: there are mainly two types of foundations such as shallow and deep foundations. A shallow foundation transfers the load to the soil near to the surface. Here the depth of the foundation is generally less than its width. Whereas, a deep foundation transfers the load to the soil deep down. Its depth is usually greater than 3 m below the ground. Shallow foundation includes footings such as isolated footing, raft footing, combined footings etc. Whereas deep foundation consists of pile foundation, pier foundation etc. Punching shear in structural elements such as slabs and foundations. A type of failure mechanism, namely punching shear, takes place due to the action of shear under concentrated loads. The concentrated loads act on a smaller area in the members. As a result, column act against the slab and slab will fail. The main mechanism of failure is that the column punches through the slab. This failure mechanism is called punching shear. Two objectives in this study: punching shear analysis of different footings are studied. Along with punching shear, parameters affecting the stability of the foundation are also evaluated. To study the behavior of buildings supported by different types of foundations. To study the behavior of footings by changing different factors affecting its performance. To study the behavior of structure for parameters like soil bearing capacity, bending moment, shear force, footing stress, eccentricity, punching shear. 3. Methodology. The methodology of the study is as follows. Modeling and analysis of a 12-storied building in ATABS software, exporting column loads from ATABS to SAFE software, modeling and designing of different footings in SAFE software, optimization of different types of footings, analysis of isolated footings under eccentric loading, study on eccentricity in isolated footing, evaluation of footings in weak soil, punching shear analysis, comparison of results. 4. Modeling of building. The modeling of the building is done using the software ATABS. The model description are as follows. IJERT 10 is 060224 www.ijert.org 497. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org M30 grade concrete Fe415 grade steel no of bays in X and Y direction equals 6 span of bays equals 4 m beam size equals 230 mm x 500 mm column size equals 500 mm x 500 mm slab thickness equals 120 mm International Journal of Engineering Research and Technology, IJERT, ISSN 2278-0181 Volume 10 Issue 06, June 2021 V-Load Calculations Table 1. Dead load, as per is 875, 1987 Part 1, Specifications Brick wall floor finish load 13.8 kN/m superscript 2 1.2 kN/m superscript 2 Table 2. Live load, as per is 875, 1987 Part 2, Specification Commercial Building Load 3 kN/m superscript 2 Fig.1. Plan the concrete grade and rebar grades of beam, column, and slab are safe as per is 456, 2000 when analyzed in A tabs. Fig.2 3D model Fig.3. Exported loads from A tabs. The column loads are first calculated in A tabs by using equivalent static analysis. Here for the further analysis the combination of dead load and live load acting under each column has been determined. That is, the axial loads on each footing are calculated. After calculating the loads, they are exported from ATAB software to CSI Safe software. The different types of foundations are then modeled using the calculated axial load that acts under each column. The dimensions of each footing are calculated with the help of the axial loads obtained. For that the safe bearing capacity of different soils should be taken into consideration. 6. Modeling of footings in SAFE. Different types of footings are designed and analyzed in SAFE based on a variety of parameters. 7 types of footings are selected for the study and are optimized. Each parameter is then evaluated for every footing. The results are tabulated and compared in detail. IJERT 10 is 060224 www.ijert.org 498. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org A Isolated Footing International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig.4. Optimized isolated footing. The dimensions of the footing are then optimized in such a way that the punching shear ration falls below 1 and the soil pressure is below the assumed safe bearing capacity of the soil. The optimization is done for making the structure more economic and safer. The optimized dimensions are shown below. After optimization, the self-weight of the footing got reduced by 19% when compared with the assumed dimensions. The optimized dimension is shown below, C1, 2.5 mx 2.5 mc2, 2.9 mx 2.9 mc3, 3.3 mx 3.3 mc4, 3.4 mx 3.4 mc5, 3.5 mx 3.5 mb raft footing Fig.6. Optimized raft with drop footing. The figure shows the optimized raft footing with and without drop. After optimization, the size of raft without drop obtained is 25.9 mx 25.9 mx 0.7 m. For raft with drop the size obtained for footing is 25.9 mx 25.9 mx 0.5 m and the size obtained for drop is 1.0 mx 1.0 mx 0.5 m. As per is 1080, a minimum depth of 50 cm shall be used for mat foundation. It was found that the self-weight of raft foundation is reduced by 21.27% when drop is added. See pile foundation Fig.5. Optimized raft without drop footing Fig.7. Optimized pile foundation. The optimized pile foundation is shown here. The No. of piles under the pile cap is obtained by dividing column load by pile capacity. In CSI Safe, pile cap is modeled and piles are given as point springs having stiffness of pile. The optimized pile cap details for the pile foundation are shown in the following figures. IJERT 10 is 060224 www.ijert.org 499. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig.8. 2 pile cap, depth equals 800 mm, Fig.12. Optimized combined trapezoidal footing Fig.9. 3 pile cap, depth equals 1000 mm, Fig.10. 4 pile cap, depth equals 800 mm, D-eccentric footing Fig.13. Optimized strap footing 7. Punching shear analysis. Punching shear analysis of the different types of footings are done in SAFE software. The punching shear value between 0.9 to 1 gives the most economic and stable foundations. Analysis of punching shear is done in normal soil and in weak soil. The study then progresses by comparing the results and determining the foundation suitable for each type of conditions. A punching shear analysis in normal soil Fig.11. Optimized combined rectangular footing Fig.14. Punching shear ratio of isolated footing IJERT 10 is 060224 www.ijert.org 500. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig.15. Punching shear ratio of combined rectangular footing Fig.16. Punching shear ratio of combined trapezoidal footing Fig.19. Punching shear ratio of raft with drop footing Fig.17. Punching shear ratio of strap footing. Punching shear greater than 1 lead to unsafe sections and is negligible in case of strap footing. It is because the strap footing has increased reinforcement and strap beam connection for preventing punching shear failure mechanism. B. Punching shear analysis in weak soil Fig.18. Punching shear ratio of raft without drop footing Fig.20. Punching shear ratio of pile foundation. Punching shear is limited to 0.9 to 1 to get optimum depth of raft and is not applicable in the case of pile foundation. In pile foundation, the column cannot punch through the slab as the foundation is supported by piles. Hence it is not applicable. 8 Results. The building model is analyzed using equivalence static analysis. The column axial loads obtained from this analysis are exported from ATABS and then imported to SAFE. Using these column axial loads, different footings are modeled, designed, and analyzed. Punching shear analysis for different footings are done for parameters such as soil bearing capacity, bending moment, shear force, and footing stress. IJERT 10 is 060224 www.ijert.org 501. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org A punching shear vs soil bearing capacity International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 D. Punching shear vs footing stress Fig.21. Punching shear vs soil bearing capacity B. Punching shear vs bending moment Fig.22. Punching shear vs bending moment C. Punching shear vs shear force Fig.23. Punching shear vs shear force Fig.24. Punching shear vs footing stress 9. Conclusions. In this study, a 12-story building is modeled and analyzed in ATABS. The column loads are then exported to SAFE. The different kinds of footings are then designed in SAFE. Optimization of the footings are done by considering SAFE bearing capacity and punching shear. Punching shear value just below 1 gives the perfect optimization. Value greater than 1 or very much less than 1 will result in failure of structure. The effect of punching shear is negligible in case of strap footing and pile footing. The internal force of footing is irrespective of punching shear ratio. Punching shear mainly depends on the depth of the footings. Soil bearing capacity. With increase in soil bearing capacity, the punching shear ratio decreases 0.081% for isolated footing, 0.01% for raft footing, 0.16% for combined rectangular footing and 0.11% for combined trapezoidal footing. Bending moment. With increase in punching shear ratio, the bending moment increases 0.94% for isolated footing, 5.74% for raft footing, 0.5831% for combined rectangular footing and 1.48% for combined trapezoidal footing. Shear force, with increase in punching shear ratio, the shear force increases 0.29% for isolated footing, 1.39% for raft footing, 0.31% for combined rectangular footing and 0.43% for combined trapezoidal footing. Footing stress, with increase in punching shear ratio, the footing stress increases 0.91% for isolated footing, 5.25% for raft footing, 2.92% for combined rectangular footing and 1.48% for combined trapezoidal footing. For every increase in punching shear ratio, combined rectangular footing has the lowest increase in bending moment, 0.5831%. For every increase in punching shear ratio, isolated footing has the lowest shear force increase, 0.29%. For every increase in punching shear ratio, raft footing has the highest stress increase, 5.25%. IJERT 10 is 060224 www.ijert.org 502. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 X References 1 Zia Abdeen. S. Punker 1, M. H. Kalhar, Anjum Algar, Kush Appa MK4, Analysis and Design of Raft Foundation IJERT, International Journal of Research in Engineering and Technology EISSN, 2319-1163 Volume, 06 Issue, 10 Oct 2017 2 Thursdays RAUNG 1, Dr. K. Thuy Tun, Parametric Study on Foundation of Regular High-Rise RC Building Under Seismic Load International Journal Scientific Engineering and Technology Research, ISSN 23198885 Volume 03, Issue. 10 May 2014, pages, 2089-2095. 3 Sagar Satish Tayad, Mukund M. Mahajan, Foundation in Refilled Soil International Journal of Innovative Research in Science, Engineering, and Technology, Volume 3, Special Issue 4, April 2014 4 J. P. Chaliawala, Hitesh K. Damilia Hiten El Kini, A Review of Parametric Study of Raft Foundation International Journal of Advanced Engineering and Research Development, Volume 1 Issue 12, December-2014 5 Nithya Chandran J., Abhilash Rajan, Soni Syed, Seismic Analysis of Building with Underground Stories Considering Soil Structure Interactions International Journal of Emerging Technology and Advanced Engineering Website www.ijtai.com, ISSN 2250-2459, ISO 9001:2008 Certified Journal, Volume 4, Issue 11, November 2014, 6 Haytham Adnan Sadek Mohammed Salim Taha, Structural Design of Raft Foundation Qatar University College of Engineering, Course, Design of Reinforced Concrete Structures, 7 is 456-2000, Plain and Reinforced Concrete Code of Practice, Bureau of Indian Standards, New Delhi 8 is 875, Part I-2 3 1987, Code of Practice for Design Loads for Buildings and Structures 9 is 1893, Part I 2002, Criteria for Earthquake-Resistant Design of Structures, General Provisions for Buildings 10 SP 16 Design Aids for Reinforced Concrete 2 is 456 1978. IJERT 10 is 060224 www.ijert.org 503. This work is licensed under a Creative Commons Attribution 4.0 International License.